Okay, so here's an example of an average acceleration problem where acceleration is assumed to be constant. So it's important to keep note of that. This particular example is assuming that A stays constant throughout the whole entire motion. So if you want, pause the video, write these parts down in your notebook if you like. Other than that, I will go ahead and start it. So here we have a car that starts at rest in the diagram and in the statement, and its initial position in the diagram is -10. So this is really important to notice. It's important that you should not assume that everything starts at 0. So read a question or anytime, refer to a schematic. So in this particular problem, again, the car starts at 0. It will accelerate to the right as indicated by the acceleration vector at a rate of 2.4 meters per second square. And then it reaches a speed of 15.6 meters per second at some unknown position, aka xf here. Okay, so you have A, B, C, D, E, F here. So I'll just knock it out one part at a time. All right, so let's do it. Part A asks us to find the time required to reach the instantaneous speed, aka the magnitude of the velocity or the absolute value of the velocity. So it's important to note that because it asks for speed, you do not need to really worry about direction here as you do your math. All right, so let's knock out the time. In order to find time, I would first, for this part, start with the average acceleration function. What's the change in velocity over the change in time? But it asks for time, so let's go ahead and get delta t by itself first. So algebraically, in order to get t in the numerator, it's important to multiply both sides by t. And then the t's on the right side of the equation will cancel out, and that'll leave you with a times delta t is equal to change in v. But again, this part asks us to find change in time. So to get change in time by itself, we need to divide both sides by a, and that will look like this. And the a's on the left side now of the equation will cancel out. So here we have an expression for change in time, which is change in velocity over a. So it's important to write these down if you need help with the algebra stuff. Okay. All right. So from here, it's pretty much plug and chug for part A. The diagram gives us two velocities. The final velocity at some unknown position, which is 15.6 meters per second, and the initial condition is 0 because it starts at rest. So we plug in the values from the diagram. Here Vf is 15.6 meters per second. You notice that you don't have to really worry about the sign because it's just the instantaneous speed. And then the initial velocity here is simply 0 because it starts at rest. I just put it in just for visual purposes here, but really if you're doing your work, you don't need to write the 0. And then the acceleration, as indicated in the diagram, it is a positive 2.4 meters per second square. So here I have 2.4 meters per second square in the denominator. So if you simplify using your calculator, you should get a value of 6.5 seconds. Okay, so that'd be the answer to part A. All right, let's do B. B wants us to find the distance required to reach 15.6 meters per second. So in this diagram, you notice here that it gives us the initial position. It gives us the final position as an unknown. But this particular question asks you to find distance. So really, because the object is moving in one direction, in this case moving to the right, the distance would simply be the magnitude of the displacement. The only time you really have to be careful is if object turns around. But in this case, a car starts at 0, it's accelerated to the right, so it's not turning around. So really, the magnitude of your displacement is the distance if an object only goes one way and never turns back. Okay, so it's important to make note of that. So therefore, I can bust out the displacement function, which is vit plus 1/2 at squared. Again, I can use this because the car is only going one way. So if I find delta x, the absolute value of that would just give me the distance. So from here is really just plug and chug. You know a lot of the values already. Again, for visual purposes, I put in vi is equal to 0 meters per second as a placeholder there. The time in this case is 6.5 seconds as we found in part A. So this 6.5 seconds came from part A. So if you didn't watch part A, rewind the video. And then the acceleration is 2.4 meters per second square as indicated in the diagram. And the time here again is 6.5 meters per second. And don't forget to square this particular quantity as the function states it is t squared. So if you punch all this out in your calculator, you should get a value of 50.7 meters. All right. Now that's not the only way to do it. Okay. There are different ways to do these types of problems. It all depends on how familiar you are with these kinematics functions. So hopefully, if you're watching this video, it'll help you kind of see that there are different approaches. Pick one that you like to use, and then hopefully stick with it. All right. You can also use this particular function, which is time independent. So you notice here is vf squared minus vi squared equals 2a delta x. This is one of the essential kinematics equations when a is constant. From here, it asks us we need to isolate for delta x because the part b asks us to find distance. To isolate for delta x, we divide both sides by 2a, and that's what I have here on the left side. And from here, we can just plug and chug. The final velocity is given to us as 15.6 meters per second. Do not forget to use parentheses and square this particular quantity. And then minus 0. You can put the square if you want, but 0 square is just 0. So I just put 0 there just so you can visualize vi being 0 or vi squared being 0. Okay, and then 2 in the denominator gets carried down, and then the acceleration is given to us as 2.4 meters per second square. And if you plug this stuff in your calculator, you should get 243.36 in the numerator, and the denominator is simply 4.8, and if you divide those two numbers, you should get 50.7, which validates that it does work out to be the same magnitude, which is 50.7 meters. Again, I'm not concerned with direction here because the question is asking for distance. Okay, and your third option, without using calculus, because this is a constant acceleration function, you don't need to get too fancy by usage of calculus. So you can just do algebra stuff. To find the displacement, or in this case the distance, we can set the two average velocity functions equal to each other. In this case, to get delta x by itself, I would multiply both sides by delta t. That would bring the delta t in the denominator on the left side up to the right side. And I like to use parentheses just to separate my terms. Alright, so here we notice that we have everything. Vf is given as 15.6, vi is 0, the 2 is part of the function, so I just carry that down. And then the time we got from part A, which is 6.5, and if you multiply that out, you will also get a magnitude or a distance of 50.7 meters. So which strategies you employ, that is entirely up to you. Hopefully you know more than one. This way it just helps build confidence. Part C. This one is a little tricky. It's important that you read what's being asked of you. It asks for the car's position, not displacement, not distance. Like, where is the car at 2 seconds relative to this number line? The car initially starts at a position of -10, which means it's to the left of the origin, aka the 0 point. So where is it as it travels to the right? So let's go and find this. You can go ahead and use the displacement function. From the displacement function, we can plug in a lot of stuff here. Vi being 0, A being 2.4. Here the time is 2 because I've decided to start my problem from the very beginning where the object's at rest. So that would indicate that the time is 0. Times equal to 0 to times equal to 2, which implies that the interval of time is 2 seconds. So that's why all my t's down here are substituted with 2 seconds. And then from there, we can just cancel out the first term. 0 times 2 is just stupid. You can just simply leave that out in your scratch book if you like. Again, this is just for the sake of explaining things to you folks. And then 1/2 and 2 times 2.4 times 2 squared, which is 4, will give you a value of 4.8. But it's important that you cannot stop here, because what you just found is the displacement. The question is asking for a single point, not the change in position, but for a single point. So it's important that you just cannot stop here. You have to realize that what you just found is delta x. But you also know that delta x for a one-dimensional analysis is final position minus initial position. So from here, you need to find xf, because it says the position x of t at 2 seconds, which indicate that it is xf that you are trying to find. Okay, and not xf in the diagram. Xf in the diagram occurs at 6.5 seconds. But this particular part wants us to find where is it at 2 seconds. So don't carry over that misconception. So delta x can be substituted for 4.8 meters, which we just found. Xf is our unknown. And then we want a minus, but this is where good habits are gonna pay off. Xi is a -10. So it's important to substitute an xi as -10 and use parentheses, because hopefully that'll indicate that you have a negative sign outside, and then you have a negative sign inside the parentheses. So therefore, multiplying a negative and a negative will give you a positive quantity. So therefore, this next line is going to look like this. For the 4.8 on the left side remains constant. XF is your unknown. A negative times a negative is a positive. But then to solve for XF, you have to move this negative 10 to the left side of the equal sign, or subtract 10 from both sides. So it'll look like this. Therefore, 4.8 minus 10 will give you a negative 5.2 meters. So your final position is negative 5.2, which is, to the right of negative 10. Okay, so that is your position. So it is important that you understand that you were asked to find position, not displacement. But you need to know displacement in order for you to find the final position. The other way to do it simply is to start with the displacement function again. But go ahead and right away, you can go ahead and break delta x into xf minus xi. So here, instead of delta x, I will replace delta x with what is equal to, which is xf minus xi. And then because it asks for a position at a certain time, that indicates that you need to find xf. So therefore, to find xf, you need to get rid of this negative xi. So you need to add xi to both sides of the equal sign. So therefore, this negative xi here, I would just move to the right side of the equal sign, and by doing so, it changes sign to a plus. And then from here, I can just plug a bunch of stuff in. But keep in mind that for this particular problem, I started from 0 second, which indicates that vi is 0. So if vi is 0, 0 times t is 0. So that term I just kind of left out of my work in this part, just in case you're wondering. So I start with the 1/2, and the a is 2.4, t is 2 second, and then I added. But keep in mind that the xi value itself is negative 10. Okay, so the lack of detail is gonna mess with your answer if you don't pay close attention to when to plug in a negative value, when when to plug in a positive value. The initial position is to the left of the origin, therefore it's negative 10. All right, so if you simplify your stuff, the first term here with all the 1/2, 2.4 times 2 squared will give you 4.8, and then you're going to add a negative 10, which will give you negative 5.2 meters. So because position is a vector, the negative sign indicates that it is left of the 0 point, so you're good here. But as you can see, your answer should be very consistent regardless of how you do your work. Okay. All right, let's knock out D and E. For part D, this one's pretty straightforward. This one asks for the change in velocity. It doesn't ask for final or initial. It asks for like how much it has changed. So you notice here it's asking for delta V. And how do you know it asks for delta V? Because the word change implies the symbol delta and velocity for V. So know when to group things and then know when to break things up. Here I don't need to break anything up. So I'm actually going to start with the average acceleration function. And then I will keep delta V as delta V in the numerator divided by the change in time. And because I'm trying to find delta V, I will multiply both sides by delta T. Multiplying the right side by delta T will cross that out. And then multiplying A times delta T will simply yield A times delta T, which is equal to delta V. But we already know what A is, and then we know what our change in time is based on this particular part D. Your acceleration is given in the diagram as 2.4 meters per second square. Delta T is 1.5. The reason it's 1.5 is because the time interval is from 1.5 to 3. So the difference is 1.5 seconds. So you can do 3 minus 1.5 to get 1.5. You can do 1.5 plus 1.5 to get to 3. It doesn't really matter how you think about it, okay? But the change in time here is simply 1.5 seconds because the difference of these two these two times, okay? All right, so if you do that, delta V is going to equal to 3.6 meters per second. But because velocity is a vector, I went ahead and indicate that the increase in velocity is to the right, aka in the eastward direction. All right, so that's that. Let's do part E. Part E asks us to find the distance covered during the second. This type of wording tends to confuse kids. The second simply imply from 1 second to 2 seconds. So from 0 to 1 second would be the first second. From 1 to 2 seconds would be considered the second. And if for future problems, if a question asks you from 2 to 3 seconds, the wording would be the third second. So this type of wording is essential to your success in terms of being able to know what the starting time is and the ending time. Okay, so the second implies that you need to start at 1 and you go to 2. So therefore, let's go ahead and do this. So you can find the displacement function. You can apply the displacement function again from 1 to 2 seconds. But VI at 1 second is 2.4, because in the diagram, if the initial velocity is 0 to start with, 1 second later, it will increase to a value of 2.4 meters per second, because that's what acceleration tells you about your velocity. Each second, your velocity changes by 2.4. In this case, it's getting bigger by 2.4 because it's speeding up. So after 1 second of acceleration, my velocity should be 2.4. And I start at 1 because that's what the question is asking for. And you notice here t is just 1 second, because delta t is simply 2 minus 1, and then 2 minus 1 is 1 second. And then the next term is easy. The 1/2 is part of the function, the acceleration is given, and then the interval, again, is just 1 second. Don't put in 2. You have to pay attention that from 1 to 2 seconds, it's a difference of just 1 second. So this is usually where kids go wrong, because they might just plug in the biggest number. So it's important to take the difference in the 2 times. So 2 minus 1 is 1 second. All right, other than that, it's just calculator work. So if you do that, you should get 2.4 plus 1.2, which will give you 3.6 meters. Because it asks for distance, I can just stop there. I don't need to give a direction. Again, delta x is the same as distance if an object moves one way. In this case, it does. So therefore, because I just found delta x, 3.6 would be the magnitude, aka the distance. So I don't need to give any directions. Okay, so I'm done with 3.6 meters. All right. The other way to do it is to break it up into 2 chunks. You can start the problem at 0 and go to 2 seconds. If you do that, this is what the work would look like. So if you start at 0 second, your initial velocity would then be 0, but then your change in time would be 2, because 2 minus 0 is 2 seconds. And then everything else kind of stays the same here. So the only difference here is that I started my problem from 0, I went to 2. If you do that, you should get a distance of 4.8. But you can't stop there, because the question didn't ask you to find the distance from 0 to 2. It asks you to find the distance from 1 second to 2 seconds. Okay, so what you can also now do is find the distance travel, or aka the displacement travel, from 0 to 1. Or if you start again from 0, your initial velocity starts at 0. The change in time here would just be 1, because from 0 to 1 second is just 1. So if you do all this work again, just for the second time interval, it tells you that during the first second you have covered 1.2 meters. But it's important that you understand what to do with these 2 numbers. So here's a visual for you. Okay, this red line indicates the distance traveled from 0 to 2 seconds. So as my work indicates, from 0 to 2 seconds, the car has covered a distance of 4.8 meters. Now, the second work that I did here, from 0 to 1, tells you that during the first second, the car has only covered 1.2 meters. But the question is it's asking from 1 to 2. So really just using common sense, if 0 to 2 is 4.8 and 0 to 1 second is 1.2 meters, the leftover would have to be the difference. So in this case, it would just be 3.6. 4.8 minus 1.2 would give you 3.6. Okay, I don't like the second strategy because it's a bit more work. I like this first strategy a lot better. But using this first strategy, you have to make sure that you plug in the right initial velocity. And you have to recognize that the problem starts at 1 second. Because the problem starts at 1 second, the car is already in motion. Because it's already in motion, you have to know that the initial velocity is 2.4 meters per second for this problem and not 0. It's a common mistake that kids make. They'll put VI as 0 because the diagram said 0. But really, they're overlooking the fact that t is 1 second and not 0 second. Okay, I hope that helps. If you need to, rewind it and listen to that again. All right, let's do the rest of the parts. Okay. Part F asks you to find the average velocity between 1.5 to 3 seconds. So here are a couple of different strategies you can employ. The first one I like for this one, acceleration is constant. So to me, it's super easy to find VF and VI. So I will do that. I will go ahead and find VF. VF at 3 seconds would simply be 2.4 times 1.5. Okay. Excuse me. I found the VF at 1.5 seconds. And then you can also find the VF, okay, at 3 seconds. So in this case, it would be the same acceleration. You would find the first time, which is 1.5 seconds. It tells you how fast the object is moving after 1.5 seconds. On the right side of the screen, I just found how fast the object is moving at 3 seconds. And then from there, the 7.2 meters per second would be my final velocity. This 3.6 seconds, even though it says VF here, really is my initial starting point. Okay, it's VF relative to 0 second, but really for this problem, it is now my initial velocity. So at 1.5 seconds, the object is moving at a rate of 3.6. At 3 seconds, it is moving at a rate of 7.2. So I can just plug in these values. My VF being 7.2, my VI for this problem being 3.6. Okay, again, VI is not 0 because the problem didn't start at 0 second, it starts at 1.5 seconds. So you need to find out how fast the object is moving at 1.5 second, and that value is now your initial. So 7.2 is my final, 3.6 is my initial, divided by 2, which is part of the function, and you should get 5.4 meters per second. But it asked for average velocity, it didn't use the phrase magnitude, and average velocity is a vector, so therefore get in the habit of indicating e to the right or positive 5.4 meters per second. All right, the other way to do it is simply just using the average velocity function, which is displacement over time, but then you can rewrite the displacement function for what it is. The function for delta x is vi delta t plus 1/2 at squared, and you would divide by t because delta t is part of the function. But hopefully your algebra skill is good. There's the t on the bottom, there's the t in both of these terms in the numerator, so I'm going to cancel stuff out. So make sure you cancel stuff out carefully here. That delta t is going to cancel out with the t on the bottom. And then this 1/2 at squared, t squared would imply that it's t times t. So I'm actually just going to cross out the square term, not the t itself. Okay, so be careful here. Cross out the square because you're only canceling one of the t's out. So if you do that, the whole entire function reduces down to vi plus 1/2 at. Again, the t in this term needs to stay because you're only canceling one of the t's out. And then from here, it's just plug and chug. You know vi is 3.6. Again, vi is not 0. The problem starts at 1.5 seconds, and the object is already moving at 1.5 seconds at a rate of 3.6, which we found up here. And then the acceleration is given, and then the time here would simply be 1.5. And excuse me, ignore that square right there. I canceled that square already. This is just poor work on my part, okay? That square should not be there. Okay, so I'm just going to mentally block that square out with my cursor. That square should not be there. So 3.6 plus 1/2 times 2.4 times 1.5 will give you 5.4 meters per second. And again, put east for the sake of average velocity being a vector. Okay, I hope that helps. Sorry for my little error at the end there with the square term. All right, good luck. Stay nerdy.